7:41 in the morning, a volcano that has been doing the same quiet thing for over 90 years suddenly drives an ash column so high it nearly scratches the boundary of the stratosphere. 16 minutes. 3 people died. Then silence. 7 hours later, a different country, a different volcano, the same continuous arc of crust beneath the Pacific. Sakurajima fires its 9th eruption of the year toward a city of 600,000 people. Same day, same tectonic system, and here is the part that almost nobody is talking about yet. The last time any volcano on Earth punched material to the altitude that Dukono reached today, it cooled the entire planet for more than a year. So what exactly happened on May 8th, 2026? Stay with us. Because the question is not whether something happened. The question is whether it is finished. 2 volcanoes, 1 arc, 1 day, and somewhere inside that sentence is either the most remarkable geological coincidence of 2026, or the opening line of something we do not yet have the language to describe properly. Let us start with the clock, because the clock is where this story first becomes strange. At 7:41 in the morning Western Indonesia time on May 8, 2026, the sun had barely cleared the horizon over the island of Halmahera. The sky was the pale gold of early morning in the tropics, the kind of light that makes everything look unhurried and safe. And then Mount Dukono opened up. Not in the way it usually opens up, not in the low, grinding, smoky way it's been expressing itself almost without interruption since 1933. This was different. Within minutes, a column of grey-black ash began driving upward through the morning air with a kind of concentrated energy that made volcanologists stop mid-sentence and look again at their screens. 10,000 meters above the summit, that is the number that matters. 10,000 meters above an already elevated peak, sitting at 1,087 meters above sea level. Add those numbers together, and you have an ash column reaching approximately 11,087 meters above the ocean surface. That is the altitude where the troposphere ends and the stratosphere begins in the tropical atmosphere. That is not a volcanic eruption. That is a volcanic eruption standing on its toes, reaching for a boundary that changes everything about how the atmosphere responds to it. The eruption lasted 16 minutes. 16 minutes of concentrated paroxysmal energy released from a volcano that has been in a state of continuous low-level activity for over 9 decades. In those 16 minutes, 3 climbers on its slopes were killed. Others were stranded, waiting for rescue teams to reach them through falling ash and uncertain conditions, on a mountain that had just reminded every human being on it that it was never theirs to begin with. Then it went quiet, and 7 hours and 34 minutes later, on the other side of the Philippine Sea, at 16:15 Japan Standard Time, the sun sitting low and amber over the island of Kyushu, Sakurajima did what Sakurajima does. It erupted. Its 9th explosion of the calendar year, sending a column of ash 3,500 meters above its crater, hurling chunks of ballistic rock between 1,000 and 1,300 meters from its summit, scattering ash southeast toward Kagoshima, a city of roughly 600,000 people who have developed a practiced relationship with this particular neighbor. People who keep ash cleaning equipment in their homes the way people in flood zones keep sandbags. 2 eruptions, 7 hours and 34 minutes apart, both sitting on the same continuous arc of subduction zones that ring the Western Pacific, the chain of converging tectonic plates that generates some of the most concentrated volcanic and seismic energy anywhere on the surface of this planet. Now here is something important to hold. Volcanoes erupt. That is what they do. On any given week, somewhere between 15 and 25 volcanoes are actively erupting on Earth. That number sounds alarming until you understand it is essentially the planet's normal operating state. So the fact that two volcanoes erupted on the same day is not by itself a story. What makes this a story is the specifics. The altitude Dukono reached, the arc they both inhabit, the 10 days of escalating regional activity that preceded both of them, and a question that no monitoring agency on Earth can currently answer with certainty. Are we watching two independent systems doing what independent systems do? Or are we watching something that does not yet have a clean name? That question is not going to get a clean answer today, and I want to be honest about that from the beginning. What it is going to get is the most thorough and honest examination the data currently allows. To understand why May 8th matters, you need to understand what Dukono's normal looks like. Mount Dukono sits in the North Maluku province of Indonesia, on the island of Halmahera, one of those places that does not appear on many mental maps, but sits on one of the most geologically active stretches of crust on the planet. Dukono has been in a state of continuous eruptive activity since 1933. That is not a typo. More than 90 consecutive years of uninterrupted volcanic activity, making it one of the longest continuously erupting volcanoes on Earth. It routinely produces ash plumes. The Indonesian Center for Volcanology and Geological Hazard Mitigation maintains an exclusion zone of 4 kilometers around the summit, precisely because of this baseline activity. Warning systems exist, protocols are established. Dukono is monitored and catalogued with the thoroughness that comes from nearly a century of being a known and documented problem.
On a normal day, Dukono's ash plumes reach between 400 and 1,400 meters above its summit. That is its operating envelope. That is the range within which it has been expressing itself for generations. Volcanologists who study Dukono know this range the way a cardiologist knows a patient's resting heart rate. It is the baseline. It is what normal looks like. On May 8, 2026, Dukono produced a plume of 10,000 meters above its summit. That is not an incremental increase above baseline. That is not a worrying trend line. That is an order of magnitude deviation from established behavior. If a patient with a documented resting heart rate of 60 suddenly registers 600 beats per minute, we do not call that an elevated reading. We call that a crisis. And while volcanic systems are not human hearts, the principle of magnitude deviation applies with equal force. Dukono did not exceed its baseline. It detonated past it. The eruption lasted approximately 16 minutes. Short duration for what it produced. That tells us something important about the energy concentration involved. This was not a long, slow exhale built up over hours. This was a single violent breath held for 90 years and released in a quarter of an hour. The ash column was gray-black, dense, and driven northward by upper atmospheric winds. Seismic signals associated with the event ranged from weak to strong tremor, consistent with the rapid pressurized movement of material through the volcanic conduit. Everything about the seismic and visual profile points to a release of accumulated pressure that had not been clearly telegraphed by the monitoring data available in advance. And here is where the human dimension enters. At the time of the eruption, climbers were present on Dukono's slopes. This is not as reckless as it sounds in retrospect. The exclusion zone covers the summit area, but the mountain is large and its lower slopes have historically been accessible. People climb it. They have climbed it for years. The continuous low-level activity that defines Dukono has paradoxically given some visitors a false sense of its predictability. If it is always erupting a little, perhaps it will not erupt a lot. That logic did not survive May 8th. 3 climbers were killed. Others required rescue under conditions that were still dangerous and still evolving. The gap between geological risk and human behavioral response is almost always filled with assumptions. And assumptions in the presence of a volcano with a 90-year history are expensive. The last time Dukono produced an eruption of remotely comparable scale was approximately 1570. Whether May 8th approaches that historical benchmark is still under analysis by the relevant volcanological bodies. But even the possibility that it reached volcanic explosivity index 3 territory is significant because the VEI scale is logarithmic. A VEI-3 releases roughly 10 times the energy of a VEI-2. And a VEI-2 is already not a small thing. So we have a volcano with a 90-year record of controlled, bounded, continuous activity that on one morning in 2026 produced an anomalous paroxysm that killed 3 people, sent ash to the edge of the stratosphere, and then went quiet. What changed in the system? Where did that energy come from? And does the fact that Sakurajima erupted 7 hours later have anything to do with it? There is a category of volcano that volcanologists refer to informally as restless systems. These are not dormant volcanoes that occasionally wake up. These are volcanoes that never truly sleep. They grumble and vent and occasionally throw things, maintaining a state of persistent semi-eruption that makes them simultaneously less alarming in daily life and more dangerous than their quieter neighbors. Sakurajima is one of the most famous restless systems on Earth. It produces hundreds of eruptions per year in active periods. Kagoshima, the city of roughly 600,000 people sitting directly across the Caldera Bay from it, has ash evacuation drills and dedicated roof cleaning infrastructure the way other cities have building fire codes and snow removal programs. Sakurajima is woven into daily life in southern Kyushu in a way that is both remarkable and to an outside observer quietly extraordinary. The eruption at 16:15 Japan Standard Time on May 8, 2026 was the 9th eruption of the calendar year from Sakurajima's Minamide crater. In peak years, Sakurajima has produced over 1,000 discrete eruptions in 12 months. 9 through early May is not frantic, but it is not suppressed either. The system is active and running. What the May 8 event produced was a plume rising 3,500 meters above the summit crater, notable but not exceptional for Sakurajima in an active period. The plume drifted southeast carrying ash toward the Osumi Peninsula and toward the greater Kagoshima metropolitan zone. Ash advisories were issued. Residents were reminded of the same protocols they have practiced many times before. Close windows, wear masks if going outside, watch for reduced road visibility. But here is the detail that matters more than the plume height. The ballistic ejecta. During the eruption, Sakurajima threw chunks of rock between 1,000 and 1,300 meters from the summit crater. Ballistic ejecta are the projectiles of the volcanic world. Unlike ash, which travels on the wind and follows atmospheric conditions, ballistic rocks are hurled on fixed trajectories directly from the explosion. Their range is a direct measure of explosion intensity. The energy required to throw a multi-kilogram fragment of rock over a kilometer from a crater at altitude is not trivial. 1,000 to 1,300 meters of ballistic range indicates a genuine explosive event, not routine gas venting. This was not Sakurajima clearing its throat. This was Sakurajima delivering a real punch. The historical anchor for Sakurajima that every serious discussion eventually reaches is 1914. On January 12th of that year, Sakurajima produced one of the most significant eruptions in Japanese recorded history, a VEI-4 event that released enormous volumes of lava, connected the island of Sakurajima to the Osumi Peninsula, and fundamentally changed the geography of southern Kyushu. May 8th was not 1914. That needs to be stated clearly. But the timing of May 8th relative to what Dukono did 7 hours earlier is the thing that no one can explain cleanly. 2 of the most persistently active volcanoes on the western Pacific Arc, both producing significant explosive events within a single calendar day. Not both being their worst selves, but both being notably and simultaneously expressive on the same arc of crust, against a backdrop of other regional events that when laid out on a timeline begin to look less like scattered data points and more like something approaching a pattern. Here is what we know, stated plainly without interpretation. On May 8, 2026, Mount Dukono on the island of Halmahera in Indonesia erupted with a plume height approximately 7 to 25 times greater than its established 90-year baseline. The eruption lasted 16 minutes, killed 3 people, and sent material to the approximate altitude of the tropical tropopause. On the same day, 7 hours and 34 minutes later, Sakurajima in southern Japan produced its 9th eruption of the year with a plume of 3,500 meters and ballistic ejecta reaching over a kilometer from the crater. Both volcanoes sit on the continuous western Pacific subduction belt. In the 10 days preceding May 8, the same regional system produced the following. Mayon volcano in the Philippines generated pyroclastic flows on May 2. A magnitude 6.0 earthquake struck eastern Samar on May 4th. A magnitude 5.5 event occurred near Baganga on May 7th. And a seismic swarm was recorded in Papua New Guinea on May 8th itself, coinciding with the two eruptions. That is a sequence of significant events spanning roughly 3,500 kilometers of arc compressed into 10 days. The default scientific interpretation of any such sequence is that active regions produce active events and the Western Pacific is always active. This is true. The Philippine Sea Plate is always subducting. The Pacific Plate is always pushing. Volcanoes along this arc are always doing something. The background noise here is higher than almost anywhere else on Earth. So when several events cluster in a short window, the simplest explanation is that you are seeing normal activity in a high-activity environment and your pattern-seeking brain is connecting dots that were not meant to be connected. That might be the right answer. But the simplest explanation has a specific problem in this case. And the problem is Dukono's altitude. When a volcano that has been producing consistent low-level activity for 90 consecutive years suddenly generates an order of magnitude anomaly without clear precursor warning, the simplest explanation earns a raised eyebrow. Consistent systems that deviate strongly even once carry information. The question is what kind? There are two frameworks for interpreting what happened on May 8th. The first is coincidence at an elevated baseline. Under this model, the Western Pacific Arc is in a period of slightly heightened overall activity and the events of the past 10 days are all independent expressions of that elevated baseline. They are not causing each other. They are not signaling each other. They are simply more likely to occur simultaneously because the conditions that produce each of them individually have all been slightly elevated. The pattern is an artifact of perception. The second framework is regional stress state shift. Under this model, something has changed in the broader tectonic stress distribution along the Western Pacific Arc over recent weeks or months. Multiple systems are responding independently but simultaneously to a changed mechanical environment. They are not directly triggering each other, but they are all responding to the same upstream change. The way multiple trees in a forest drop their leaves at the same time not because they are communicating but because they are all experiencing the same seasonal shift. The difference between these two models matters enormously. One implies that the system's stress state is shifting in ways that could continue to express itself through further events. And that is not a comfortable thought. The atmosphere above your head is not a single thing. It is a stack of distinct layers, each with its own chemistry, its own temperature gradient, its own rules about how air moves and what happens to particles that enter it. We live at the bottom of the lowest layer, the troposphere. This is where weather happens. Where clouds form, where storms develop, where wind bends trees and rattles windows. The troposphere is constantly churning, mixing its contents vertically and horizontally on timescales of days and weeks. Anything injected into the troposphere, ash, pollutants, water vapor, eventually gets scrubbed back out. Rain washes particles down. Turbulence disperses them. The residence time of material in the troposphere is measured in days to weeks. Above the troposphere sits the stratosphere. Between them lies a boundary called the tropopause. The tropopause is not a wall you can see or feel. It is a transition zone where the temperature gradient that drives vertical mixing in the troposphere reverses. In the troposphere, temperature drops as you go up, warm air rises, cool air falls, and that convective engine keeps the layer in constant motion. At the tropopause, that gradient flips. The stratosphere is warmer higher up, which means air in the stratosphere is stable. It does not convect. It does not churn. Material that enters the stratosphere does not get washed out in days. It stays. It spreads horizontally on global wind patterns and it persists. The residence time of particles in the stratosphere is measured not in days or weeks but in months to years. In the tropics where Indonesia sits, the tropopause occurs at roughly 11 to 12 kilometers above sea level. On May 8, 2026, Dukono sent material to approximately 11,087 meters above sea level. That is the tropopause zone. Not comfortably below it, not clearly above it. Right at it. On the threshold. In the zone where volcanologists and atmospheric scientists are now watching satellite data and asking whether any significant fraction of the erupted material, particularly the sulfur dioxide, made it into the stratosphere where it could spread globally and persist for months, or whether it topped out just below the boundary and will be washed out in the coming weeks like a normal tropospheric eruption. The answer to that question is not yet confirmed. The satellite data is being analyzed. But the fact that it is a question at all, that Dukono reached the altitude where the question needs to be asked, is itself significant. In June of 1991, Mount Pinatubo in the Philippines erupted in one of the largest volcanic events of the 20th century. A VEI-6 event that injected an estimated 20 million tons of sulfur dioxide directly into the stratosphere. That SO2 reacted with water vapor to form sulfate aerosols, tiny reflective particles that spread across both hemispheres on stratospheric wind patterns and persisted for over a year. Global average temperatures dropped by approximately half a degree Celsius. Disrupted monsoon patterns. Changed agricultural yields across continents. Altered weather at a planetary scale from a single volcanic event. In January of 2022, the Hunga-Tonga-Hunga-Hapai volcano in the South Pacific erupted in an event so fast and explosive that it produced a pressure wave that circled the globe multiple times, detectable on barometers everywhere on Earth. The Tonga eruption injected an unprecedented volume of water vapor into the stratosphere, and researchers are still working out the full accounting of its atmospheric effects. Both events share a critical feature with what Dukono did on May 8. They sent material across the tropopause into the stratosphere where it could act on global scales. The difference, and this is important, is the scale of material injection. Pinatubo's 20 million tons of stratospheric SO2 dwarfs anything Dukono produced on May 8. Dukono is a smaller volcano. Even if a fraction of its ejecta crossed the tropopause, the mass loading of stratospheric aerosols from this event is almost certainly not comparable to Pinatubo or Tonga. This is not a global climate event on the scale of those eruptions. But here's the thing about thresholds. The mechanism that made Pinatubo and Tonga globally significant is not a mechanism that activates only above some arbitrary mass threshold. It is a mechanism that activates when material crosses the tropopause. The question of whether Dukono triggered that mechanism, even weakly, even partially, is a question that applies specifically because it reached the altitude it reached. If Dukono had topped out at 8,000 meters, we would not be having this conversation. At 11,000 meters, the question has to be asked. And that brings us to an uncomfortable place. Not what Dukono did on May 8th, but what Dukono could do if this behavior continues or escalates. Let us run the hypothetical forward because volcanologists do this regularly and it is a legitimate analytical tool. On May 8th, Dukono's plume reached approximately 11,087 meters above sea level, right at the tropical tropopause. Now imagine the same eruption produced a plume 2 to 3 kilometers taller. Not dramatically more energetic in total volume, but with enough additional vertical velocity to push material clearly and unambiguously into the stratosphere at 13 or 14 kilometers altitude. At that altitude, sulfur dioxide does not wash out in weeks. It converts to sulfate aerosols and spreads on the Brewer-Dobson circulation, the large-scale wind system that moves stratospheric air from the tropics toward the poles. Those aerosols reflect incoming solar radiation, reducing the energy reaching the Earth's surface. The residence time for those particles at 13 to 14 kilometers is typically 1 to 3 years. Every day those aerosols are present, they are acting as a partial sun shade for the planet beneath them. The mass of material Dukono erupted on May 8 is not Pinatubo. We need to hold on to that. A Dukono-scale event that fully entered the stratosphere would produce a far smaller aerosol burden than Pinatubo's 20 million ton injection. But here is where the analysis becomes genuinely unsettling. The sensitivity of the climate system to stratospheric aerosol forcing is not linear. Small injections can have disproportionate effects under certain conditions, particularly if they occur at a time when the climate system is already under stress, or if they are followed by additional injections from other eruptions in rapid succession. Think about that last part against the backdrop of what we are discussing. Multiple active systems on the same arc. A 10-day cluster of events across thousands of kilometers of the same tectonic boundary. A question about whether the regional stress state is elevated. If Dukono is part of a broader period of heightened activity, and if that activity includes another eruption or series of eruptions that approach or cross the tropopause, stratospheric loading could become significant even if no single event approaches Pinatubo. This is not a prediction. There is no monitoring agency currently predicting that Dukono will repeat or escalate its May 8 behavior. The volcano's behavior after the event returned to its characteristic low-level activity. But the question of what changed in the system to produce a 90-year anomaly in 16 minutes remains genuinely unanswered. And unanswered questions about what drove an anomaly are uncomfortable precisely because they prevent confident statements about whether the anomaly could recur. There is a useful distinction in volcanology between what are sometimes called open vent systems and episodically reawakening systems. A reawakening system is a volcano that goes dormant between major eruptions, builds pressure in silence, and then produces a catastrophic release. Long periods of quiet followed by sudden explosive resumption. These volcanoes are terrifying precisely because the quiet does not mean safe. It means charging. Open vent systems are different. They are always venting. The conduit between the magma chamber and the surface is always at least partially open, which means pressure does not accumulate the way it does in a sealed system. The continuous outgassing of an open vent volcano is in a strange way a pressure relief mechanism. It is never fully sealed, so it never builds to the kind of overpressure that drives a truly catastrophic eruption. Dukono is an open vent system. It has been venting continuously since 1933. By the standard model of open vent behavior, it should not produce paroxysmal events of the magnitude we saw on May 8. The plumbing is open. The pressure should not accumulate to the point where a 16-minute burst sends an ash column to the tropopause. And yet, the volcanic explosivity index is a logarithmic scale. This is important and frequently misunderstood. A VEI-3 event does not release 3 times the energy of a VEI-2. It releases approximately 10 times the energy. A VEI-4 releases roughly 100 times the energy of a VEI-2. Each integer step is an order of magnitude. This means that Dukono's baseline activity, sitting somewhere around VEI-1 to 2, is separated from a potential VEI-3 event by a factor of 10 to 100 in terms of energy release. That is not a bad day. That is a fundamentally different mode of behavior. The statistical significance of this comes from the length of the baseline. When a volcano has been erupting unpredictably, a large event fits within the range of expected behavior. But Dukono's 90-year record of consistent low-level activity has established a pattern so stable that any deviation from it carries outsized statistical weight. In statistical terms, the longer and more consistent a baseline, the more significant any departure from it becomes. A 90-year baseline of bounded behavior followed by an order of magnitude outlier is not something that standard probabilistic models assign a high likelihood to. The monitoring community is now asking what changed. Whether the magma supply rate beneath Dukono has increased. Whether a fresh batch of more volatile rich magma has intruded into the system. Whether structural changes in the conduit altered the pressure dynamics in a way that allowed accumulation despite the open vent configuration. These are the right questions and they do not yet have confirmed answers. Let us build the full timeline. Not to manufacture alarm, not to construct a narrative that is not in the data, but because the data deserves to be laid out in sequence and seen as a sequence rather than as isolated entries in separate monitoring reports. May 2, 2026. Mayon volcano in the Philippines generates pyroclastic flows. Mayon is one of the most active volcanoes in the Philippines, famous for its near-perfect cone and its history of more than 50 recorded eruptions. Pyroclastic flows are not routine venting. They are fast-moving currents of superheated gas and volcanic matter capable of flowing down a volcano's flanks at speeds exceeding 100 km per hour at temperatures that can exceed several hundred degrees Celsius. They are among the most lethal products of any volcanic eruption. The May 2 event prompted evacuation advisories for communities on Mayon's lower slopes. A significant escalation in a system that was already at elevated alert status. 2 days later, May 4, a magnitude 6.0 earthquake struck eastern Samar in the Philippines. Eastern Samar sits on the Philippine Sea Plate within the same regional tectonic framework that drives volcanic activity at Mayon and across the Philippine Arc. A magnitude 6 is not a microtremor. It is an event that shakes buildings, triggers landslides, and is felt across a wide region. 3 days after that, May 7, a magnitude 5.5 earthquake struck near Baganga in the Davao Oriental province of Mindanao. Further south along the arc but within the same regional plate boundary system. And then May 8 itself. As Dukono was building toward its 741 eruption on Halmahera, a seismic swarm was being recorded in Papua New Guinea to the south and east, extending the active zone further along the arc in that direction. A seismic swarm is not a single earthquake. It is a sequence of multiple earthquakes occurring close together in time and space, often indicating fluid movement through rock, magmatic intrusion, or stress adjustment in a complex fault system. They are signals that something is moving in the crust. By the evening of May 8, when Sakurajima had completed its 9th eruption of the year, the total regional picture looked like this. Significant pyroclastic activity in the Philippines, 2 moderate earthquakes in the Philippine Arc, a seismic swarm in Papua New Guinea, and 2 major volcanic eruptions in Indonesia and Japan, all within 10 days. All along the same continuous subduction boundary system. All at different points on an arc stretching from the southern Pacific through Southeast Asia and up through the Japanese archipelago. Individually, every single one of these events has a standard explanation. Mayon erupts. It has done so more than 50 times in recorded history. Eastern Samar gets earthquakes because it sits on a convergent plate boundary. Papua New Guinea is one of the most seismically active regions on Earth. Dukono has been continuously active for 90 years. Sakurajima produces hundreds of eruptions annually. None of these events viewed alone requires an unusual explanation. The unusual thing is the timing. The compression. The way a span of 10 days produced not one event but a cluster spanning 3,500 kilometers of the same tectonic system. The Western Pacific subduction belt is not a single thing. It is a series of interlocking tectonic boundaries that together form the most seismically and volcanically active region on Earth. The Pacific Plate, the largest tectonic plate on Earth, is moving generally westward, subducting beneath the Eurasian Plate to the north and west and beneath the Philippine Sea Plate to the south. The Philippine Sea Plate is itself subducting beneath both the Eurasian Plate to the north, generating the Ryukyu Arc and the southern Japanese island chains, and beneath the Sunda Plate to the west, generating the Philippine Arc and the volcanic systems of Indonesia. The Australian Plate is simultaneously pushing northward into the Asian landmass, driving compression through Papua New Guinea and the Indonesian archipelago. Sakurajima in Japan sits on the Ryukyu Arc generated by the subduction of the Philippine Sea Plate beneath the Eurasian Plate. Dukono on Halmahera sits on the North Maluku Arc generated by a complex interaction between the Maluku Sea microplate, the Philippine Sea Plate, and the Eurasian Plate. Mayon in the Philippines sits on the Philippine Arc generated by the subduction of the Philippine Sea Plate beneath the Philippine Mobile Belt. These are distinct subduction systems. The magma chambers beneath each of these volcanoes are fed by different portions of the subducting slab. The plumbing is not shared. There is no direct hydraulic connection between Dukono and Sakurajima. No underground pipe through which pressure in one system directly drives an eruption in the other. This is why standard geophysical models do not predict synchronization of activity across these systems. And yet the concept of stress transfer in the lithosphere is real and well documented on smaller scales. When a large earthquake occurs on one segment of a fault, it redistributes stress on neighboring segments. The Coulomb stress transfer model, a standard tool in seismology, can predict which segments of a fault system become more or less likely to rupture following a major event. This operates over distances of tens to hundreds of kilometers, not thousands. The distance between Dukono and Sakurajima is approximately 3,000 kilometers. Direct stress transfer at that scale is not a credible mechanism for synchronized activity. What is more credible, though not yet demonstrated for this specific cluster, is the concept of coordinated response to a broader regional stress state change. If the overall balance of tectonic forces across the Western Pacific has shifted, not through a single large event but through a gradual accumulation of strain over weeks or months, then multiple independent systems that were all approaching their own individual thresholds could cross those thresholds in a compressed time frame without any of them directly triggering the others. Multiple systems responding to the same upstream change without communicating with each other. The way multiple trees in a forest respond to the same seasonal shift. The scientific community has two primary competing explanations for what the May 8th cluster represents, and both deserve serious examination. The first model, which we might call the elevated baseline interpretation, begins from the observation that the Western Pacific Arc is always producing events and that the rate of events varies naturally over time. There are quieter periods and more active ones. The transition between them does not require a specific trigger. Under this model, the 10-day sequence from Mayon on May 2nd through the Sakurajima eruption on May 8th represents a statistical cluster within a naturally elevated activity phase. Each event has its own independent cause. The cluster is real in the sense that more events occurred than on an average 10-day window, but the correlation between events is not causal. They are statistically independent given the elevated baseline. This model is scientifically conservative, well-grounded in the history of volcanic and seismic monitoring, and consistent with the absence of any identified coupling mechanism between the events. It is the model that the majority of working volcanologists and seismologists would currently default to, not out of complacency but out of well-earned respect for the rate at which human pattern recognition produces false signals in complex natural systems. Its weakness is that it does not fully account for the specific anomalousness of Dukono's behavior given its 90-year record. Behavior that sits at the extreme tail of its historical distribution in ways that are not easily dismissed. Or for the broader 10-day pattern that extends beyond just the 2 May 8 eruptions and encompasses a series of smaller but cumulatively notable events across the arc that preceded them. The second model, regional stress state shift, argues that the cluster reflects a real change in the mechanical state of the Western Pacific lithosphere. Multiple systems independently approaching their individual thresholds were pushed past those thresholds in a compressed time frame because the regional stress environment shifted. The stress perturbation could have originated from a slow slip event on one of the subduction interfaces, a transient change in plate convergence rates, or a deep intraslab seismic event whose rupture propagated stress into surrounding arc systems without producing a surface signature large enough to draw immediate attention. This interpretation requires a regional scale stress redistribution event whose nature has not yet been identified. That is a weakness that needs to be named plainly. But it is not mechanistically implausible. The relevant physics exist. The question is whether they operated in this specific case. Under this model, the elevated activity may not yet be over, and the coming weeks could produce further events in the same regional system. Neither model is definitively supported or excluded by the currently available data. Both are consistent with what we observe. The distinction between them may only become clear in retrospect after months of continued monitoring. Human beings are pattern recognition machines. We evolved in an environment where the ability to detect patterns, even in noisy data, carried direct survival value. The rustle in the grass might be a predator. The darkening sky might mean rain. The pattern-seeking brain that could extract signal from noise lived longer than the one that required absolute certainty before acting. The problem is that the same cognitive machinery that kept our ancestors alive on the savanna is now being applied to questions in volcanology and seismology where the signal-to-noise problem is vastly more complex and where the consequences of false positives, of seeing a pattern that is not there, can include unnecessary panic, misallocated resources, and eroded public trust in scientific institutions. The clustering illusion is the tendency to perceive patterns in random distributions. Flip a coin enough times and you will eventually get 8 heads in a row. That streak does not predict the next flip. The coins have no memory. But if you are watching coin flips in real time and you have seen 7 consecutive heads, your brain insists the next one will be heads too. This is not rational probability assessment. This is your pattern recognition system running hard in the presence of sequential data. Volcanic and seismic events are not coin flips. They are generated by complex physical systems with memory, with stress accumulation, with thresholds and feedbacks. Some clustering is genuinely real. Aftershock sequences are a real form of clustering where an earthquake genuinely increases the probability of further earthquakes in the near term. Volcanic unrest often genuinely precedes eruptions. Not all patterns are illusions. But the global eruption rate of 15 to 25 active volcanoes per week means that on any given week there are dozens of volcanic events occurring somewhere on Earth. The Western Pacific concentrates a disproportionate share of these events. Given a high enough background rate and a large enough geographic area, clustering of events within short time windows is not just possible. It is mathematically expected even if no event influences any other. The question is always whether the observed clustering exceeds what you would expect from the background rate, and by how much. For the May 8 cluster, the answer is probably yes. The clustering appears elevated above pure background, but not so dramatically elevated that it definitively excludes a statistical explanation. The pattern is real in the sense that it is unlikely to be purely chance. The cause of the pattern remains genuinely unknown. And the distinction between those two statements is exactly where we need to live intellectually right now. On May 7, 2026, at 15:14 UTC, the Sun produced an M-class 2.6 solar flare. The timing relative to the Dukono eruption and the Sakurajima eruption will not be lost on certain corners of the internet, and it would be intellectually dishonest to not address it directly. The M2.6 flare was not Earth-directed. The active region on the Sun responsible for it was not oriented toward Earth at the time of the eruption, meaning that the primary output of the flare was not flowing toward our planet. Crucially, there was no associated coronal mass ejection detected in connection with this event. Without a CME impact, the geomagnetic environment at Earth on May 7th and 8th was quiet. There was no enhanced geomagnetic activity, no elevated atmospheric electric field, no measurable energetic particle flux at ground level that could be proposed as a triggering mechanism for terrestrial geological events. The temporal correlation between the solar flare and the volcanic eruptions exists as a matter of arithmetic. The flare happened, the eruptions happened, the gaps between them are what they are. But correlation without mechanism is not causation. It is coincidence dressed in numbers. Every time a cluster of seismic or volcanic events occurs, the timing gets compared to solar activity, to lunar position, to any number of external variables that happen to have available data series. Some of these correlations are real and mechanistically understood. But a non-Earth-directed M-class solar flare with no associated CME sits well outside the range of mechanisms that could plausibly interact with deep crustal volcanic processes. Every physical interaction between cause and effect has an energy budget. The cause must deliver energy in sufficient quantity at the right location through a credible mechanism to produce the observed effect. Effects do not arise from insufficient causes. You cannot start a car engine by blowing on the hood. You cannot trigger a volcanic eruption by dimming the lights in the room above it. The energy released in a significant volcanic eruption ranges from approximately 10 to the 14th power joules for a moderate event to 10 to the 16th joules or higher for a major event. To put that in physical terms, a 10 to the 15th joule eruption releases roughly the equivalent of 250,000 tons of TNT. This is not energy that responds to subtle external nudges. The most commonly invoked artificial triggering mechanism involves HARP, the High-Frequency Active Auroral Research Program facility in Dukono, Alaska. HARP's maximum radiated power is approximately 3.6 megawatts, equivalent to roughly 3.6 times 10 to the 6 joules per second. The energy required to meaningfully perturb a subduction zone or volcanic magmatic system is on the order of 10 to the 14th to 10 to the 16th joules delivered precisely to a target zone buried kilometers beneath the surface, shielded by rock that does not efficiently conduct electromagnetic energy. The gap between what HARP can deliver and what would be required to trigger a volcanic eruption is not a close call. It is a gap of 8 to 10 orders of magnitude, 100 million to 10 billion times insufficient energy. The monitoring data for Dukono and Sakurajima is public, published by the Indonesian Center for Volcanology and by the Japan Meteorological Agency respectively. Multiple independent monitoring networks in different countries with different institutional affiliations all show the same picture. The artificial triggering hypothesis fails the energy test, fails the mechanism test, and fails the evidence test. It deserves a clear statement to that effect, and then we move on. Because the genuine uncertainty about what drove the May 8th cluster is interesting enough without invented explanations to fill it. Strip away the fringe explanations. Strip away the cosmic coincidences and the energy budget impossibilities. Strip away the pattern recognition traps. What you are left with when you look at May 8, 2026 clearly and honestly is a legitimate and unresolved scientific question. Did the Western Pacific Arc experience a regional stress state shift in the weeks preceding May 8? And if so, what drove it? And what does it imply about how the system evolves in the coming weeks and months? Here is what we know. We know that Dukono produced an anomalous eruption that exceeded its 90-year baseline by an order of magnitude. We know this is statistically significant, not as proof of anything external but as a real deviation from expected behavior. We know that 7 hours later Sakurajima produced a notable explosive eruption with ballistic ejecta indicating genuine explosion intensity. We know these two events occurred against a backdrop of heightened seismic and volcanic activity across the Philippine Arc over the preceding 10 days. We know that multiple Philippine volcanic systems are currently at elevated alert status. We do not know whether these events are causally connected. We do not know whether they reflect a regional stress state shift or a statistical cluster at elevated baseline. We do not know whether Dukono's paroxysm represents a one-time anomaly or the beginning of a period of more energetic behavior. We do not know whether the material from the May 8 eruption entered the stratosphere or remained in the troposphere. We do not know what changed in Dukono's magmatic system to produce a 90-year anomaly in 16 minutes. These are not rhetorical unknowns manufactured to create suspense. They are genuine open questions in geophysics and volcanology that the relevant monitoring agencies and research institutions are actively working to answer. Our monitoring capabilities have improved dramatically over the past 3 decades. We have satellite-based geodetic measurements that can detect millimeter-scale ground deformation across entire subduction zones. We have seismic networks dense enough to locate earthquakes to within kilometers of their true hypocenters. We have volcanic gas sensors, thermal imaging systems, infrasound arrays, and ocean bottom seismometers. And yet on May 8, 2026, a volcano with 90 years of well-monitored continuous activity produced a paroxysm that nobody predicted. That should be humbling in a way that is not irrational fear but genuine scientific honesty about how much complexity remains in these systems. There are 3 ways to read what happened on May 8, 2026. 3 interpretive frameworks. Each has evidence in its favor. Each has evidence against it. None can currently be proven or disproven with available data. The first is coincidence. Under this reading, the May 8 cluster is a statistical fluctuation in a high-activity region. The Western Pacific Arc is always producing events. The background rate is elevated relative to most other regions on Earth. In any given 10-day window, some number of events will occur, occasionally more than average. Not because they are related, but because the background rate is high enough that clusters are statistically expected. The Dukono anomaly under this interpretation is a genuine internal variability event triggered by some internal process, perhaps a fresh batch of more volatile rich magma reaching the upper conduit, perhaps a transient structural change in the conduit geometry. Sakurajima's eruption is Sakurajima doing what it does roughly 9 times per year. The shared calendar date means nothing beyond the shared date. The strength of this interpretation is that it requires no novel mechanism and is consistent with the absence of demonstrated coupling between the events. Its weakness is that it struggles to fully account for the specific anomalousness of Dukono's behavior given its 90-year record, and for the broader 10-day pattern spanning the entire arc. The second interpretation is regional stress state shift. Under this reading, the cluster reflects a real change in the mechanical state of the Western Pacific lithosphere. Multiple systems approaching their individual thresholds were pushed past them in a compressed time frame because the regional stress environment shifted. The stress perturbation could have originated from a slow slip event on a subduction interface, a transient change in convergence rates, or a deep intraslab event whose propagation went undetected. This interpretation requires a regional scale stress redistribution whose nature has not been confirmed. That is its weakness. Its strength is that it provides a coherent framework for the entire 10-day pattern. It would predict weakly that the elevated activity may not yet be over. The third interpretation is precursor phase to a larger event. This is the most disturbing of the 3 and the one that needs to be stated clearly while being surrounded with appropriate caveats. Stating it is not alarmism. Refusing to state it would be a different kind of intellectual failure. Under this reading, the cluster represents the early stages of a regional stress loading process that could culminate in one or more large-scale events, whether a major volcanic eruption at one of the currently elevated systems or a large earthquake on one of the subduction interfaces, or a combination of both. The historical record contains examples of elevated precursory seismic and volcanic activity preceding major events. But it also contains many more examples of elevated precursory activity that resolved without a major climactic event. The ratio of false alarms to true precursors is high, dramatically, disconcertingly high. The ability to distinguish between them in real time is one of the most difficult problems in all of geophysics. If forced to a ranking, most volcanologists and seismologists would place coincidence as most likely, regional stress state shift as possible and perhaps roughly equally plausible given the full 10-day picture, and precursor phase as the least likely but not negligible enough to dismiss without sustained intensive monitoring. The asymmetry of consequences matters. If coincidence is correct and we treat it as a stress state shift, the cost is heightened monitoring and some unnecessary public communication. If the precursor interpretation is correct and we treat it as coincidence, the the cost is measured in something else entirely. That asymmetry does not justify abandoning scientific standards of evidence. But it does justify maintaining a posture of active surveillance rather than passive observation. We are now in a monitoring phase for the Western Pacific Arc. That phrase has a specific meaning. It means that the events of May 8th and the 10-day cluster that preceded them have raised the baseline level of attention being paid to this system by the international volcanological and seismological community. Data that would normally be processed in routine review cycles is being examined more frequently and with greater scrutiny. Certain thresholds for issuing public warnings have been mentally lowered not because the science has changed but because the recent pattern has provided new context for interpreting signals. For Dukono, the most important monitoring question is whether the May 8th paroxysm was an isolated event or the first in a series. The indicators to watch are seismic tremor patterns beneath the volcano, ground deformation data from satellite measurements, volcanic gas emission rates particularly sulfur dioxide, and whether subsequent eruptions show any trend toward greater energy release rather than returning to the pre-May 8th baseline. As of available reporting, Dukono has returned to its characteristic continuous low-level activity following the May 8th event. But the question of whether the magmatic system has fundamentally changed state cannot yet be answered confidently. For Sakurajima, the monitoring question is about eruption frequency and escalation. Whether the annual eruption count accelerates in the coming months, whether individual events show increasing energy or increasing ballistic range, or whether structural changes in eruption style indicate deeper magmatic involvement. For the Philippine Arc, the 4 volcanic systems at elevated alert status represent perhaps the most consequential near-term monitoring priority given the population density in those areas and the historical pattern of rapid escalation in Philippine volcanic activity. What to watch for in the coming days and weeks is a short list. Any recurrence of Dukono-scale paroxysms from Dukono itself. Any escalation in Sakurajima's eruption frequency or explosion energy. Any increase in alert levels on the Philippine volcanic systems. Any large magnitude seismic events on the Philippine Sea Plate interface. Any reports of anomalous ground deformation or gas emissions from any of the monitored systems in the region. This is not a prediction that any of those things will occur. It is a description of the signal space that the pattern of May 8th has established as worth watching carefully. Let us go back to 7:41 in the morning over Halmahera. The sun is just clearing the horizon. The light is pale gold. The sea around the island is still the way the sea is still in the very early morning before the wind picks up. And then a mountain that has been smoldering continuously for 93 years does something it has not done in living memory. It sends a column of ash so high and so fast that it reaches the boundary between the part of the atmosphere where things wash out in days and the part where they persist for years. In 16 minutes, 3 people are dead. Others are scrambling for safety in the dark cloud descending on the mountain slopes. 7 hours and 34 minutes later, the sun is low in the west over Kyushu, and Sakurajima does what Sakurajima does. But it does it on this specific day against this specific backdrop. The Western Pacific on May 8, 2026 presented the scientific community and the public with a moment of genuine ambiguity. Not manufactured ambiguity. Not false ambiguity from inadequate information. Genuine ambiguity. Multiple competing explanations, each consistent with the available data, each with different implications for what comes next, none of them yet distinguishable from the others by the evidence currently in hand. The anomalies are real. Dukono's order of magnitude deviation from its 90-year baseline is real. The 10-day cluster across multiple systems on the same arc is real. The tropopause proximity of the Dukono plume is real. The simultaneous elevated alert status of multiple Philippine volcanic systems is real. None of these are manufactured urgency or statistical sleight of hand. They are the data presented as clearly as the data currently permits. What those real anomalies add up to is the open question. And the honest answer, the one that serves you better than false certainty in either direction, is that we do not yet know. We are watching. We are monitoring. We are running models and rerunning them with May 8th incorporated as a new data point. There is a concept in complex system science called synchronization. It describes the phenomenon where independent oscillating systems, each operating according to its own internal dynamics, begin to coordinate their behavior through some form of weak coupling. The classic example is metronomes on a shared surface. Started at random phases, they eventually synchronize. Not because any individual metronome changes its fundamental behavior, but because the shared platform allows a tiny feedback between them that gradually aligns their rhythms. Synchronization does not require direct communication between components. It requires only that they share a medium through which some small influence can pass. The Earth's lithosphere is a medium. It transmits stress. It transmits slowly and imperfectly the mechanical state of one segment to another. Whether the events of May 8 represent a version of geological synchronization, multiple systems aligned by weak coupling through the shared lithospheric medium, is a question the data itself has raised but cannot currently answer. The Western Pacific is always active. That is its identity. The background noise of its existence is higher than almost anywhere else on Earth. And the events of May 8 are asking, without yet answering, whether the familiar background noise has begun to change. Not necessarily louder, but different, more coordinated than the background usually is. Synchronized in a way the instruments are detecting and the models are not yet fully explaining. The synchronization of metronomes begins slowly, almost imperceptibly before it locks. You watch individual metronomes and they look like they are each doing their own thing. And then if you step back and watch the group, you notice that the individual things they are doing have begun, subtly and without announcement, to line up. Whether the Western Pacific in May 2026 is in the early stages of geological synchronization or simply producing an elevated phase of background activity that will quietly subside is not a question that the current data resolves. What can be said with certainty is this. On May 8, 2026, two of the most persistently active volcanic systems on the Western Pacific Arc exceeded their expected behavior within the same day, within the same tectonic framework, against the backdrop of a 10-day sequence of events spanning 3,000 kilometers of the same system. The altitude Dukono reached is real. The energy Sakurajima released is real. The cluster that preceded them is real. The interpretation of all of that remains open. And open questions in geology, as in most things that matter, have a way of closing themselves in the language of events rather than the language of conclusions. We are watching. And the watching is not over.